Okay, people, I fixed my anti-space problem. Let's continue. So this is what we were saying. This is our essential matrix, epsilon, and it has 9 numbers in it. Okay, it says that take the P, take the transpose. P is a 3-dimensional vector, and if I take the transpose of it, I have, okay, 1, 2, 3 elements. Okay, and this is P, and P prime is another 1, 2, 3 elements. If I multiply this with this one, what am I gonna get? I am going to get a vector of 3 elements. So these two will produce a vector like this, a row vector, and I multiply it with this one, and it's going to produce a 0. Okay, good. If I know that these 2 points correspond to each other, this multiplication with these 9 numbers as a matrix should produce a 0. Should produce a 0. Okay, and this is called okay, essential matrix. Inside the essential matrix, remember the definition of essential matrix, it is Tx times R. Tx means the skew-symmetric matrix of the translation vector between the two cameras. R is the rotation, of course. Okay, E is called the essential matrix. Okay, there are 9 coefficients inside the E, of course, but they are defined up to a scale because there is a 0 here. I mean, whatever the numbers inside E, I can multiply all of them with 5. For example, if I multiply everything with K here, if I multiply everything with, for example, A here, all the numbers, and multiply the other side with A, the result will not change because it is 0 here. So this essential matrix is defined up to a scale. Okay, but inside the essential matrix, all I know is that there is this rotation matrix and the translation vector. So inside the rotation matrix, I know there are 9 numbers, but I know that rotation around x-axis, y-axis, and z-axis are the real numbers. So the degree of freedom of R is 3. Okay, 3 numbers come from there. Okay, and I have 2 degrees of freedom defining the direction of the translation vector. 2 numbers come from there. So a total of 5 parameters defines this essential matrix. Okay, good. Okay, if I look at this one, let's look at this one again. Let's look at this one. Okay, if P is a point, okay, if P is a point, is another point. If I multiply these two, or maybe let's do it this way. If I multiply these two, okay, this essential matrix and this one, I will get a 3-element vector. And if I think that this is a 3-element vector, L, and this is my P equal to 0. So what do I see here? L is a line, P is a point on that line. So essential matrix times this P prime would give me a line. That is the epipolar line that I'm going to make my search on. Okay, so this multiplication would produce a line for me, and if I put this point on that line, it should produce a 0, like with the homogeneous coordinates, right? So this equation essentially captures this epipolar geometry. Okay, in the epipolar geometry, what did I say? If I am going to search for this P on the other image, this is what I am going to do. Multiply that P with the essential matrix, and you are going to get the equation for this line. And do the other way. Multiply that P prime with E again from the other side, and you are going to get the line for the other epipolar line. Okay, so this essential matrix is very nice. It defines this epipolar geometry in essence, and it automatically produces these lines for us. Okay, good. So very nice result. Very nice results here. There is only one problem with the essential matrix. Okay, we don't like something that we don't like. The thing is that essential matrix works in the camera coordinate system, not image coordinate system. We don't like it. Why? Because if I take images of the same scene with two different cameras, okay, if I take images of the same scene with two different cameras, then I have my image coordinates of the whole system. I don't have the camera coordinate system. Okay, let's go back to our original image. Let's go back to our original image. Okay, let's look at this one. Yeah, I have left image and right image. I don't see any camera coordinate system pixels. All I see is okay, this point here is column number is 50 and row number is 50. That's it. That's what I see. I don't talk about millimeters in this case. I talk about the image coordinate system. But the essential matrix talks about okay, talks about the millimeters. It doesn't talk about image coordinate system. So it would be very nice if we have such an equation that talks about the image coordinates. But we can do that, right? We can do that. Remember how we transform our points in the camera coordinate system, the image coordinate system. What do? We multiply it with the intrinsic parameters, 3 by 3 matrix. Remember that one from the first two lectures of this semester? Okay, our intrinsic parameters. Inside the intrinsic parameters, we have the focal length, we have the skew angle, we have the ratio of the image pixel height to pixel width, etc. Right? So if I multiply this point P with the matrix K, I would get, let's say, hat. This P hat is in the camera coordinate system. I multiply it with this one, I would get the image coordinate system. Okay, image coordinate system. And for the P prime again, I would multiply it with K, I would get the P prime. So how am I going to put these? Okay, these are the primes, these are the heads. How am I going to put this in there? So maybe from here I can do P hat is K minus 1 times P, right? This is good. Okay, so P hat is K to the minus 1 times P, and P prime hat is, okay, let's say this is KL and KR, KL and KR, okay, KL and KR minus 1 and P prime. Okay, let's put them in here. Okay, for the P hat, I would write K minus 1, K1 minus 1 P transpose E, and for the P prime hat, I would write K R minus 1 and P prime. equal to 0. What is the size of K?
K is 3 by 3.
Yeah, K is 3 by 3, right? So essential matrix is 3 by 3. This is 3 by 3. Well, let's look at this part. Do you guys remember this one? A times B transpose. What is this? Do you remember it?
B transpose, A transpose.
Yeah, like this. So let's apply it here. If I apply it on this one, I am going to write it here. So it's going to be P transpose times K1 minus T. This is what I do. Okay, instead of saying minus 1, I would say minus 1 T. I would say K1 minus T. Okay, an essential matrix KR minus 1 and P prime equals 0. Look at this one. Look at this one that I am marking with red. 3 by 3, 3 by 3, and 3 by 3. So if I multiply all of them together, okay, I will end up with a 3 by 3 matrix. And this time the nice thing is this P and this P prime is in the image coordinates. They are not in the camera coordinate system, which is what I wanted. This is good, okay. And if I do the same thing here, okay. If I say the center matrix K minus T, transpose and inverse, okay, essential matrix times K prime minus 1, okay, this one is called, again, this is a 3 by 3 matrix called the fundamental matrix, okay. As much as we love the essential matrix, we love fundamental matrix even more, okay, because this fundamental matrix talks about the image coordinate system. Okay, this is the real deal. Fundamental matrix talks about the image coordinate system, and for most of the stereo things, if the geometry is involved, we use the fundamental matrix. Okay, it is so famous and it is so frequently used that people made songs about it. They sing about it, and I think I have that video file somewhere. Can I find the fundamental matrix song? I think it was in one of my slides. Where is it? Fundamental matrix song. Maybe it's here. Yeah, here it is.
Okay, is everyone ready? Yes, yes, okay. Right, we're recording. Okay, go.
Do you hear this? Do you hear the music?
No.
Okay, I think I need to share it with sound turned on. Let me do this. Okay. So it's a 3-minute song. Let's listen to it.
Okay, is everyone ready? Yes, yes, okay. Right, we're recording. Okay, go. The fundamental matrix used in stereo geometry. A matrix with 9 entries. It's square with size 3 by 3.
I did not go over the meanings of each number of the fundamental matrix, but at the end it has 3 by 3 elements. It has 9 elements in it.
Has 7 degrees of freedom.
It has 7 degrees of freedom because in it has the translation vector, rotation vector, also the other intrinsic camera related stuff.
It has a ranked efficiency. It's only of rank 2.
And the rank of the fundamental matrix is 2, not 3, because you multiply fundamental matrix with some numbers and you get a 0 at the other end.
Call the matrix F and you'll see 2 points that correspond. Column vectors called x and x prime. X prime transpose times f times x equals 0 every time.
Whenever you have correspondences between two images, or between the 2 points between two images, if you put the fundamental matrix in between them, it has to be 0 all the time.
The epipolar constraint involves epipolar lines. Poles multiplying f by x results in vector L prime. It's the epipolar line. The other view passing through x prime.
Using the fundamental matrix, you can get to the epipolar points, E prime and E, and all you need to do is find the null space of F. I don't think that I'm going to talk about it.
The 3-component vector of homogeneous design. The left and right null spaces of F are the epipoles E prime and E. All of the epipolar lines should pass through these. Here's a linear estimation example. Take a set of 8-point samples.
So now this is talking about how to obtain the fundamental matrix from the images, okay? Images of stereo directly without doing any camera calibration and etc. I think I will talk about this later. Maybe I won't talk about it. I think I will just show you the OpenCV procedures to obtain the fundamental matrix from images.
Graph the matrix, take the SPD, and the elements of F are in the last column of V.
Singular value decomposition will give the fundamental matrix. See, this view and this view are two different views of the same scene, stereo pair, and this guy is tracking this tip of the violin bow, right? And so he's going to draw the epipolar lines corresponding to these two. So how do you draw the epipolar lines? You produce a fundamental matrix, and you produce the line formula that I showed you, and make this drawing. So I think this is MATLAB code, but you understand the idea. So yeah, these are the epipolar lines corresponding to this point and that point.
Here we go! If you try to estimate F with a coplanar set of points, your sample set will be degenerate. That will not bring you joy. When doing the estimation, if you don't perform rank deprivation, your epipolar lines and the epipoles will not coincide. But if your scene has 3 views, the trifocal tensor is what you use. Constraints from the 3rd.
Okay, I think this is now talking about the 3-view geometry. In the 3-view geometry, you don't talk about the 2-dimensional matrices, but 3-dimensional matrices, which are called tensors, and we will not talk about them later. Okay, so this is the song of the fundamental matrix. As you see, this guy doesn't have a very good voice. he cannot hit the notes very well, but good effort. Okay, we thank him, whoever he is. Okay, so watch that fundamental matrix on, I think it is available on YouTube. Let me go back to my slides. Okay, so fundamental matrix is something that is basic, really, as the name implies, fundamental in stereo. Usually we start establishing the fundamental matrix before doing anything else with stereo pairs. Okay, and we know the formula for the fundamental matrix, right? This is the formula. Intrinsic parameters for the left camera, intrinsic parameters for the right camera, and the essential matrix is the translation vector between the left and right, and the rotation matrix between left and right. If we know all of them, we can get the fundamental matrix, but that requires us to calibrate our left and right cameras together and separately. Okay, that's a lot of work. The idea is this: can we estimate the fundamental matrix without knowing, okay, the left camera intrinsics, right camera intrinsics, the TX and R parameters of the cameras? The answer is yes. Okay, that's called the weak calibration. Without knowing the camera parameters of left and right cameras, we like to estimate these 9 numbers. Remember, these 9 numbers, they are not unique numbers, they are defined up to a scale. Okay, and this is how we're going to do it. Can anybody have a guess how we do it? I mean, you don't have to give me all the details, but you can direct me towards the solution. Doing this and this and that would produce as results.
I think the right-hand side is like a linear system.
Yeah, there's a linear system, definitely.
But when we multiply the left side, I think it will become quadratic.
No, there is no quadraticness in this one, no. Because if you remember what I did, if you multiply this one with this one and then that one, there would be a 0 here, and that would be a relation, linear relation between those. If it's a quadratic equation, then our jobs would be much tougher. So what do we know here? We know P prime, right? We don't know these 9 numbers. How do we know P and P prime? This is how we know it. This is okay. This is our left image and this is our right image. Okay, using, let me go to this. Yeah, okay, left image and right image. I run surf on this one and I run surf on this one. I found the key points and I established the correspondences. Now I know that there are maybe 9 points. P1, this one corresponds to P1 prime. P2 corresponds to P2 prime. And P9 corresponds to P9 prime, right? So I have 9 correspondences in my hand, or as many as correspondences I have in my hand. Okay? So for each correspondence, of course, I can write this. Okay? P, these numbers, and P prime. Since each one is an equation, each one is giving me some information about these numbers. If I can write 9 equations like these with the 9 correspondences, then I can find these 9 numbers, right? That's the idea. That's what we are going to do. So find the correspondences between the images. Okay. some 8 points are enough, not 9 points, but 8 points are enough, because this is not a full rank matrix. Okay, and after that, after doing that, put together all this linear system and solve that linear system. Okay, here it is. Okay, this is P, these are the fundamental matrix, and this is the P prime. If I put them together, can you understand? Do you see these two are the same thing? Okay, look at this one. U times F11, V times F21, 1 times F31. Then U times F12, V times F22 again. And then multiply all these with these numbers. This is what you're going to get. U prime times F11, okay, plus U prime, UV prime times F12 plus U times F13, etc. It goes that way. Okay, and at the end 1 times F33, and if I add them together I should get a 0. Okay, so this is just a rewrite of this matrix form into this multiplication of these two vectors. Where do I get the first vector? This vector is the unknowns, all the elements of the fundamental matrix, and this one is from the correspondence of 2 points between two images. Okay, and for each correspondence I can write one of them. So all I need is 8-point correspondences. So what can you tell me what's happening here? 1, 2, 3, 4, 5, 6, 7, 8. Where is F33? I don't see F33 here. Where is F33?
You say that it has 8 degrees of freedom. So we can, I don't remember the word.
We take it as 1.
Yeah.
We take it why? Because we are not going to find unique 9 numbers, okay? Because whatever the solution you have, I can multiply it with a constant number, and that's the solution too. So why don't we pick F33 as 1 and find all the rest 8 numbers that's going to be unique. Okay, so we assume F33 is 1, so we put a 1 in here, 1 in there. Okay, since this one is 1, all the additions are going to be times 1 is going to be 0, so I take the ones to the other side, so they will be equal to -1. They all are. Okay, so with 8-point correspondences I have this nice linear system. 8 unknowns, these are all knowns. Okay, solve the system and you are going to get your 8 unknown fundamental matrix elements and put a 1 in there, and so you get your fundamental matrix. Okay, good. So this is how you get your fundamental matrix. Again, we didn't do any explicit camera calibration. We don't know the intrinsic camera parameters or the extrinsic camera parameters of the two stereo systems. Okay, so that's why this is called weak calibration. We don't know everything about the cameras, but what we do here is good enough for getting the fundamental matrix. Yes, Selma, you have a question?
I missed the part. How did we, on the right hand of the equation, how did we set it up for all -1s?
You mean this? Remember, this was 0, right?
Yeah.
If I make this 1, okay, if I make this 1, multiply this one with this one,
Okay.
this one, and I am multiplying 1 with what? That's the +1, right? So all of these multiplications +1 equal to 0. So I take -1 to the other side because it doesn't have any unknowns in it. So I do everything. I do the same thing for all 8 rows, and this is what I get. Any other questions?
I used it in homework one. I used that one, take one to other side of the equation.
Oh, okay, good. Okay, so these are, I mean, most people are kind of stressed about these kind of matrix stuff, or they think that they don't know enough linear algebra. There is nothing to know, okay? I am telling you everything that you need to know with these slides. Just these are just basic matrix multiplication stuff, and sometimes you need new information. We give you those, okay? Nobody is supposed to know all the details about matrix algebra, okay? And when the time comes to use them in the real world problems, you don't do this kind of derivations. You just use them. In fact, let's look at these. What the OpenCV offers us for the stereo calculations and the fundamental matrix. Okay. Well, I am going to skip this one. Maybe we'll come to this one later. Essential from fundamental. Okay, that's a good one, right? How do you calculate the essential matrix from the fundamental matrix? Remember, essential matrix is TXR. Fundamental matrix is K minus T, TXR, and K minus 1 prime. K minus 1 prime. Okay, like that. Okay. So how would you calculate the essential from the fundamental matrix? If somebody gives me the fundamental matrix, and if somebody gives me these 2 intrinsic parameters, then I can output it, right? So I get the fundamental matrix, I get the K1, and I get the K2. And if I know these 3, okay, if I know these 3, this is essential matrix, right? Then I can get the essential matrix out of it. And another procedure, if you have the R and T between 2 cameras, you can get the essential matrix out of it. Okay, R1, T1, R2. Can somebody explain me this? Okay, this is what is essential? T times R, right? How about these? What are we talking about here? Oh, that's a good question. I am proud of myself. What did I say? If you have this
Sorry.
T, if you have this T and R, you get the essential matrix. Okay? If you have T and R, you get the essential matrix. And this one says that get the essential matrix from RT, but it needs R1, T1, R2, T2. What are these R1, T1, R2, T2?
Isn't the rotation and the displacement of distinct cameras, both of them?
Selman, could you talk a little bit louder?
Oh, okay, sorry. Is it the rotation and transform matrix for each canvas, or
Exactly. So what is the difference between these two then?
it's decomposed?
These are the translation vector between these 2 cameras and the rotation matrix between the cameras. These are the camera calibration parameters with respect to the real world. Okay, so I calibrate my camera separately. Okay, I calibrate my camera separately. Then, using these rotation and translation vectors, I can come up with these 2 and then the essential matrix. Okay, and then from essential to fundamental, of course, what you're going to need from essential to fundamental, you give the essential and you give these 2, and it will calculate the fundamental. That's it. And this one is interesting. Fundamental from projections. If I have two projection matrices, one for the left camera and one for the right camera, projection matrices, what is projection matrix? K R T, right? This is the projection matrix. Intrinsic parameters, rotation matrix, and the translation vector. KRT is the projection matrix. If I give you the left projection matrix and right projection matrix, it's going to give me the fundamental matrix. Okay, good. There are some other stuff related to motion, but is somebody asking a question?
Yes, I have a question.
Yeah.
Question that you asked, I think, essential form RT. It takes an array, take T1 and T2 as an input, but we, in essential metrics, we only talk about Tx. It was our baseline.
Yeah.
Because our camera is only rotated in x-axis.
Yeah.
Can we, in that function, can we change y coordinates?
Well, both of those cameras has to be in this